Hi, this is Scott Sims. I'm here to demonstrate Project 3, building a RPM tachometer for propeller blade. I'm actually going to start off by going through the wiring because I have a little weird setup just to get this to work. So let me cover that first, and I'm going to expand this so we can see a little bit better and we don't need to see me right now while we're doing this. So I have this on two separate breadboards because it was the way that I found to get it to work the best. And we have an IR emitter receiver pair. So starting off here, this black thing is the photodiode or phototransistor. And what we're going to have is that's going to be powered by 5 volts running up this rail here. And that's going to go into this resistor here. And this is a 3.2 kilo ohm resistor. That's going to go into the long leg here of the photodiode. So it's reverse bias. Also in series with that is this green path here. So this green path sits in between the resistor and the leg of the photodiode or the phototransistor here. And that's running all the way back down this rail to this yellow line here. So the white line again is the 5-volt power supply. And the yellow line here is going to go to pin 3 on our Arduino, and I'll explain what that does in a second. So whenever infrared light hits the phototransistor, that makes it act like a switch. It kind of turns on so that current can flow through it over here back down to ground, and this is just ground. So it allows it to complete the current. When no infrared light is incident on it, you can think of it as the switch is turned off. So no current can flow through all the way down to ground. Instead, it's going back down the path of this green line here to the yellow wire here, which goes to pin 3. And pin 3 is just monitoring the voltage that it sees. So if no infrared light is incident on the photodiode, current can't flow through it, so it has to flow back down through this green path here to our yellow line here to pin 3. So pin 3 should see more or less all 5 volts being generated. When infrared light is incident on this, again, think of it as a switch that turns on, current can flow. Remember, current always wants to go the path of least resistance. Pin 3 on our Arduino has a very high impedance, meaning it resists the flow of current. So whenever this is turned on, instead of going back down the path to pin 3, it will just want to complete the circuit and go to ground because that's the path of least resistance. So that means barely anything's going back down this path to pin 3, and it should see a voltage drop. So that means anytime that there's something in front of the photodiode blocking it from getting infrared light, this is turned off. So current has to flow back down to pin 3, and it should see a high voltage. When infrared light is incident on the diode, this is turned on, allowing current to go to ground instead of pin 3, and pin 3 should see a drop in voltage. So that's how we can tell when the propeller is in front of it or not in front of it. So if it's in front of it, we should see a high voltage at pin 3 because current can't go to ground. When the propeller is not in front of it, we should see a low voltage at pin 3 because current can flow all the way to ground. So, and then here is our IR emitter here. This is a very simple circuit. It's just going the 5-volt power supply of the Arduino to, I think this is a 220 ohm resistor, to the infrared LED all the way back down to ground. And I found best to get this to work when the sensors are pointed directly at each other like this. Having them side to side more or less does nothing, but when the tops of the sensors are pointed right at each other, that's when it works best. So I use my son's magnet tiles to kind of build a tower so that I can have them pointed just like this, and the propeller blade will go in between them. So let me set all that back up real quick, and then we'll go through the code. Okay, so I have everything wired back up again. And again, there's a gap in there. You just have to think that the two sensors are pointing just like this at each other, and then the propeller blade will go right in the middle of them too. So there is a gap. I just turned the IR receiver upside down, and it's pointing down towards the table at the IR emitter, which is pointing up. And like I said, the blade will go in between. Okay, now that we know the wiring, let's kind of go through the code and see how this all works. So here's our main here, and like I said, pin 2 is going to be the constant 5-volt power supply for the IR receiver. That's again because the true 5-volt power supply on the board is going to the IR emitter, so we're using pin 2 to be another 5-volt power supply. Pin 3 is our sensor. Remember, this is going to see when voltage is high or low, depending on if the propeller blade is in front of the IR receiver transmitter pair. I made a propeller just out of cardboard that I stuck to a DC voltage, DC motor. So it's nothing fancy, and again, it only has 2 blades. So we're going to keep track of that. I have it such that we calculate the RPM every 1 second, and we transmit every 1 second. And then the stop threshold here is how we can tell that there's more or less nothing in front of the IR receiver transmitter pair, and RPM can just drop to 0. Here I have a global blade pass count. This is a global volatile, and basically this is how we're going to calculate RPM. We're just going to keep track of how many times that we've seen the blade come in between the IR receiver transmitter pair, and then we need to keep track of the last blade pass time, so the last time that we saw it pass, and you'll see where this comes into play. And then the rest of these are just kind of some bookkeeping variables that we need to make sure states where we want it to be. We're going to be sending everything over Wi-Fi via UDP. So we have our object there to manage that. And then we're going to use a task queue, task queue function, or queue task function. I always mix those up. Basically, a queue of tasks to do, and those tasks are functions that will be executed. So we are going to model a task as a struct that has a function to be executed. We're going to keep track of, it's going to be preloaded with how often that specific task needs to be executed. Like we said, we're going to calculate RPM every 1 second. So once we load up a calculate RPM task, we'll make sure it's tracked here. And then we'll also keep track of the last time this was executed, since again it should be done every 1 second, so we can keep track of the last time it was to make sure that the interval is good. And then here I'm forward declaring the 2 tasks that we need to do, which are calculate RPM and then transmit it. And then we'll pre-populate our task queue here with our function. So again, our function, which I just realized I didn't cover, task function here is just an alias for a pointer to a function that returns nothing and takes in no arguments. So all the necessary logic it needs to run is already contained in the function itself, and you just need to execute it. So for our task queue here, we're pre-populating with the calculating RPM function. The interval here is RPM calculation interval, and the last time it was executed, 0, because we haven't executed yet. And then it's the same premise here for transmitted RPM. We get the size of our task, which right now is 2, and then we're going to be calculating the RPM by counting how many times the blade has come in between the transmitter-receiver pair. So we need something that will keep track of that, and that was what this global variable was, this blade pass count. So something needs to keep incrementing that. And we're going to do that with an ISR, an interrupt service routine function. And this is what it's going to do. This is the ISR function. It's just going to increment the blade pass count every time that it sees it. So when an interrupt service routine sees that it needs to be triggered and execute the interrupt service routine function, this is the function that gets executed. This is what it does, and we'll talk about how this gets registered. For our calculate RPM function here, it's simple calculation. We need to get the blade pass count, and because this is being incremented by the interrupt service routine, it is shared data. And because it's being incremented by the ISR, which operates on interrupts, we first need to disable interrupts to make sure that this doesn't get altered while we're trying to access it. So we get our own copy of it, and the same thing with this last blade pass time, and then we enable interrupts again. So we're synchronizing on that shared data. This is how we calculate to see that basically no blade has passed through the IR receiver transmitter pair in a while, and we know that RPM can just go to 0 because there's nothing there. That's not really the interesting one. Instead, what we have here is calculating the actual RPMs, where the revolutions is just the total count of blade passes that we've seen divided by the propeller blades, and we'll have 2. So if we've seen 10 counts and I have 10 blades, then we know one side of the blade has gone around 5 times. And then we calculate RPM, revolutions per minute. So it's just literally the total revolutions divided by the minutes, so RPMs. And that's how we calculate RPM. And then our other task was transmitting our RPM. Again, we're transmitting over UDP, so this is pretty simple. We're just getting our current time, and then we're making a string payload here of our current time plus whatever the current RPM was, and then we're sending it across UDP. So we've pre-populated our task queue. So the main loop will be what executes each task in the task queue. So this is our function to start that for the main loop. And so that's the main loop's job. And again, the ISR, the interrupt service routine's job, is to just increment the blade pass count, and that's all it does in the background. Good. So this is how we set everything up. Again, our pin 2 is what's going to be the constant 5-volt power supply for the receiver. So we're just setting that up. So pin mode for pin 2 here, and we're setting that up to output, and we're writing digital high, so the 5 volts always. And then pin 3, our sensor pin, is what's reading the high and low voltage depending on the phototransistor. And we've set that to input. And then everything else here up to this point is same code from Project 2. I'm not going to go over this in depth. If you're interested, go back and see my video on Project 2 that covers this. But at a high level, it's setting up Wi-Fi, so connecting the Arduino to Wi-Fi, beginning a UDP listener on a config port, which I'm using 12345. And so that's setting up wireless communication. Finally, before we go to our main loop, we wait for somebody to connect, a remote client to connect over UDP and supply a Unix timestamp so that we can synchronize the clock on the Arduino based off of that. Once that happens, then we set this ready to transmit global state to 1, and then we're ready to go. And actually, I'm realizing I don't truly need that. I'm not using it anymore. I had used it in the main loop here, but I guess I took that out, so it's actually not needed here. But this is blocking until somebody connects and gives a Unix timestamp. To round out the rest of our setup function here, remember the count blade pass function is going to be our interrupt service routine function, this thing that just increments the blade count. So we need to register that function. So we simply attach interrupt to our digital pin, our sensor pin. That's the one reading high or low. If it's high, that means that there's something in front of it, in front of the receiver, the propeller. And so you want to increment the blade count. And when it's low, there's nothing in front of it, so we don't want to increment. So we attach our digital sensor pin 3 to the rising voltage. So when we see a rising voltage, that's when we want to increment the blade pass count here. And then we just run our scheduler, and everything should work as should be, where everything's transmitted over Wi-Fi. So let's see that in action. I'm reusing the same UDP client I used for Project 2. So again, if you're interested in seeing that code, go see my video on Project 2. I won't be covering that. But let me plug in the Arduino and power it up here. And again, for my motor, nothing fancy here. It's just a DC motor here that I just put a piece of cardboard on, no, high tech. And I just have that running to its own battery pack here so I can turn it on and off. So it's just battery pack to breadboard to the DC motor. Okay. So when we're ready to run the code here, what we'll do, let me open up a terminal. This here. And to run my UDP client, I just have a pre-made code here, and that will execute. And then we see our graph come on here. Let me make this a little bit bigger. I don't want to, let me shrink this down so we can still see that I'm putting the propeller in there, hopefully. And then we have a graph here. So now I'm going to turn on my high-tech propeller here. And then we are in front, and we can see that RPM has gone up. And we're getting a little over 1200 RPMs. And then I move it away, we should see it drop to 0, and make sure that logic is working. And then we can put it back in here. And it's interesting to see that it's still continually dropping, starting off well over 1200 and coming down. Not sure exactly why that is. I do hear my motor struggling a little bit. Not sure if it's coming up on feed, how well the motor's sounding. But yeah, it definitely sounds like, and I can visually see that it's losing power as well too. So again, if I move this away from it, we should to drop to 0, and then we can put it back in, and we can see it go back up. Good. And so that is the presentation for Project 3. Thank you.